Hey, welcome back everyone to Advanced SQL. So what we're going to do in this video is to talk about one particular example, a single example that's a bit more extensive, and the discussion will, I think, fill one video just right. And as the course progresses, we will have more such videos where we will focus on one particular use case, one particular example, and then take the time to discuss only this one example. The more constructs of SQL we collect and the more stuff we have in our hands as tools, the more interesting the use cases and the more interesting the discussions and the example scenarios can become. And the more we will take advantage of that. So let's see what's on the menu today. Some alien window. Okay, so this is about a particular programming problem that you can find as one of the tasks of the ACM ICPC yearly programming contest. The ACM International Collegiate Programming Contest, held somewhere on this planet every year, collects thousands of participants, student participants, that try to compete in the quick and elegant solution of given programming problems. The problems that we are looking at now is one that has been posed in the South American regionals. So the ICPC is a competition that starts out regionally in all sections of the world, where the best qualify to be advanced to some continental competition when the final really gathers everyone for some global competition. All right, but in the South American regionals 2007, there was one particular task given, one programming task, and that was the finding seeds problem. All right, so when the designers of this problem came up with this task description, they probably didn't have SQL as in mind as one particular language in which you could solve and attack this problem. But it will be perfectly possible, and we will see how. Okay, so this is about finding seeds in a cinema, and as you can see, this is a pre-COVID-19 task description because the friends are eager to sit close together. Okay, so there are K friends are going to the movies and they try to sit close together because they are late for tickets. They were probably not sitting in a single row, really adjacent to each other, but they try to minimize the area of the rectangle in which they will find K free seats. So if K is 5, K friends going to the movies. If this is the seating plan of the movie and the current reservation status, all of the black seats have been taken already, they're occupied, then this would be the minimal rectangle, the minimal size rectangle of seats that has still at least K equals 5 free seats available. So any other rectangle that you could draw in this seating plan would either have at least 6 or even more than 6, as an area of more than 6. So this would also be a rectangle featuring 5 unoccupied free seats, but it would have an area of 3 times 3, 9. So the friends would be even more separate from each other, and that's not their goal. They want to find the rectangle with minimum area that has K free seats. That's the ACM ICPC finding seat problem. It's one of the easier problems. Okay, so when you look at such an ACM ICPC program description, what you would typically receive is a textual input, some text format that specified the current problem instance. And the problem instance would be, of course, a value of K, so how many friends are going to the movies, and the current status of the seating plan. And you can see here that the ICPC designers have specified an ASCII, a textual-based description of the seating plans. So this would be one row of the seating plan, and these are free seats. The first 3 seats in this row would be free, and these 2 seats are taken. They are marked with an X. In the next line, we would find the next row. In the next line, we would find the last row. I think this should be self-explanatory. So 3 lines describe 3 rows of seats in a cinema. Okay, X marks an occupied seat. Okay, so that would be a valid textual description, and that's all good and well. But before we can unleash the power of SQL, we would of course have to read this, parse this, and transform this into some tabular form. And this table seats would be my proposal for one possible tabular representation of the seating plan. So we would have as many rows as there are seats in the seating plan. So I think this is 5 times 3. 5 times 3 seats would be encoded in this ASCII textual seating plan. So we would have 5 times 3, 15 rows in table seats. All right. In each row, we would represent one seat. We would encode its row and column, and its Boolean taken status. Okay, so let's see. In the first row, first column, that seat is not taken. It should be free, and that's the dot up there in the corner. Let's have a more focused spotlight here. That's the spot right there. Okay. And in the first row, the column for that seat would be taken. And that's exactly this X I'm highlighting here. Okay, so that would be one possible representation, tabular representation, on which we can build our SQL-based finding seats solution. Okay, so how to parse such a textual description into a tabular format. As you will see during the course, we will have many of such textual problem instances that we need to parse. You will find many of these in the assignments, so it makes sense to invest some thought on how you would parse elegantly and generally such textual input format in a SQL environment. And one such possibility would be the query, or a sketch of a query that you are shown here on this slide. So we would of course make the seating plan and its ASCII textual based format somehow available to the system. We could copy it using the copy from construct of SQL from the file system, but for demonstration purposes we just put it here into a pSQL variable, so that under the variable name $cinema we would find this particular textual seating plan representation. Okay. So I think this could be a job for a string to array conversion. A string to array conversion that first splits the string at the new lines, at the rows. Okay, so that's what we are doing here. We are reading the cinema textual string and we are splitting it at the new lines. This would yield an array of strings, and that would be an array of 3 strings actually, because we are splitting at the new lines. Okay, so what we would get here is an array of 3 strings. And actually you can see that array of 3 strings down here at the bottom. That array of 3 strings, 3 strings would be ordered in a well-defined fashion. The first element of the array would be the first row. The last element of the array would contain the last row of seating codes. Okay, to keep this nice implicit order while we process the array in the query here, we would unnest this 3 element array. This would yield a 3-row table, and to keep track of the row order, which is relevant here of course, we would use with ordinality. Okay, so in each of the rows of our table, each of the 3 rows, we would find information, a string, a string of, in this case, 1, 2, 3, 4, 5, a string of 5 letters together with its position, with its row position inside the seating plan. Okay, so XS is an array of 5 characters. Pos is the position of that particular row of seats inside the seating plan. Okay. This is going to be parsed further because we now want to separate the 5 seats inside a row into individual seats. Recall that each seat should be represented by a single individual row in our final tabular representation. So that's what we're doing in a second step now. So these X's, they have to be split up into individual characters. And that's a job again for string to array. Okay. So here, the row.access, we will look at the current row and its 5-character string that encodes the seats, and we would split it after every character. So this would yield a 5-element array. Okay, all right. So that we can access the row variable here at this particular point, we would use the lateral keyword to indicate that we are indeed referring to a row variable that has just been introduced left of this comma. Okay, so good style to use lateral in this query, although we weren't required because, as you know, there's an exception to the rule. This is a set returning function, and we could have accessed the row variable row anyway. So, but good style dictates make that explicit and use lateral in this case. Okay, so that would be an array of individual seats split up after each character. We will turn this into a table, okay, with a set generating function unnest, and inside the table we would make the position of the seat, the seat X inside that row, we would make that explicit again with a with ordinality pos column. Okay, so row.pos would be the row position of that seat. Col.pos would be the column position of that seat. X itself would be a dot, or it would be an X. It would be the encoding of one single seat. Okay, now we have everything we need to compile the seats table. We would just use the row pos, the column pos, and of course the seat status, which, as you can see here, we very straightforwardly map from text representation into a Boolean representation. So whenever the X character is indeed the occupied seat symbol, capital X, then this comparison yields true, and that indicates a taken seat. Okay, so that would be our seat plan parser. What we get out of this is a 3-column table with pos, column, row, column, and taken status indicator. Okay, so we can see that over in the editor. Okay, so you see that you will find this particular example in its own file. So whenever such an example exceeds a particular size, you will find individual extra files that are only talking about this one particular example, and this will be the rule in the upcoming course sections when the examples get larger. Okay, and as you can see, this is a quite nice example at this particular point because it's demonstrating lateral. It's demonstrating the use of lateral table functions of unnest and regex split to table, for example, but also of generate series. Okay. With ordinality, and as we will see when we compile this larger query, it will also use with, so common table expressions. So that's a quite nice grab bag of SQL features that we've introduced in the recent videos, and they enable us to find a quite nice solution to the finding seats problem. Okay, so let's first introduce the seating plan and some value k, for example 5, as we've done on the slide. All right, and here's the seat parser. There's not much to be said actually, because it's just the seat parser from the slide that we've just discussed. It will build a seats table, or a seat CTE table, a common table expression that contains the row, column, and taken status information. Okay, right. So you see that the query is going on a bit further, and we will talk about these bits in a minute. But just let's check that the seats CTE, the common table defined here, contains what we expect it to contain. So comment this and then just run the query. Okay, so that's a 15 rows table for this particular instance of the seating plan with 5 rows. No, with 3 rows and 5 columns. That's just the expected size, and you see that all the row and column indices are occurring here. And indeed, the one seat that we had a closer look at in row 1, column 4 is indeed taken. Some others are not taken. This is the tabular encoding of the seating plan. All right. So let's take that back and prepare for the further discussion. Okay. So I think we are already in good shape, and we could discuss a general query plan on how we want to attack the finding seeds problem using our SQL setup here. So what would be the query plan? So I would suggest to first, now that we know the tabular encoding of the seating plan, it should be very easy to determine its extent. So how many rows, how many columns are found in the seating plan. That should be a simple maximum computation inside the rows and cols column of the seeds table. Okay, so once we have that, once we know the extent, the size, the dimension of the seating plan, we would now do a generate and test method, or you could also call a brute force method that we are applying here. Inside that seating plan, we would generate all possible seating rectangles, all possible rectangular seating areas that could hold our K seats. Okay, so we would generate all possible northwest or upper left corners and all possible southeast or lower right corners of such rectangular seating areas. And for each of such generated rectangle, we would just scan all the seats that are inside that rectangle and then count the number of free seats. If that number of free seats exceeds K, or is at least K, then that's a possible candidate that we would like to keep. Okay, so we would keep it in the form that we just record its upper left northwest corner and then just recall its width and height, which is just the information that the ICPC contest requested from us. Where is that rectangle located, how wide and how tall is the rectangle, and this is the information that we would keep. There could be many rectangles that actually can fit K free seats. Okay, of course we would try to find among these qualifying rectangles, we would try to find the rectangle with a sufficient seating space, but of course with minimal area. Okay, so this is the plan. I think it just reads like a plan that any generate and test or any enumeration method of problem solution would use. Nothing is really special regarding SQL here, but all of these steps are easily expressed and rather straightforwardly expressed using SQL. For example, the generate case. So generate all the possible seating rectangles. How would that look like in SQL? So yeah, it would be just this select from where block. Let's assume that the extent, the dimension of the seating plans are actually available in the rows and cols values here, or the rows and cols names. Okay, we will of course compute these, but now assume that behind rows and cols we can find 3 and 5 for the particular seating plan example that we are looking at. Okay, then we would try to generate all the possible top left or northwest corners. And this would just be done by using these two generate series here. Okay, we would just enumerate all the possible rows and all the possible column coordinates inside the seating plan. Okay, and once we have these, we would generate all the southeast or bottom right corners by enumerating all the coordinates that are row-wise below the northwest corner and that are column-wise right of the northwest corner. And you can see how we achieve that. We would just use two further generate series here that do not start at 1, but they would start at the current northwest corner, the coordinates of the northwest corner. We can do that and refer to these because we are using lateral here. So the row variable that have been bound at this particular point, they are already available here because we are using lateral. Okay, so that would lead us to all the possible southeast corners. And now we would have the northeast and the southeast corners, and we would just return them. Maybe in some nicely grouped fashion where the two row and column values that make up the northwest corner are being held in their own row value, and the same is true for the southeast corner. It would be a 2-column row value which holds the southeast corner here. Okay, of course this would generate quite a lot of possible rectangles that we are considering here. This is actually the number of rectangles that would be generated by this generate procedure. That's quite a number. And of course, in the real implementation of the query, we would try to make sure to also implement a test, a filter that would get rid of most of these rectangles very early on. Okay, I think it's time again to switch over to the editor. All right. So we have seen that part already. This is a given. We have the tabular representation of the seating plan. Now recall that the query plan started with the task of finding the extent, the dimensions of the seating plan, so the maximum row and column numbers, and that's what we are just doing in this 2-line query. We are looking at the seat plan, we are extracting the maximum row and the maximum column numbers. This will be a single row table returned because we are doing aggregation here, a single row table, and it will be available to the rest of the query under the name extent with columns, rows, and calls. Okay. Okay, so now let's enter the generate phase. Okay, let's enter the generate phase because we know that the extent of the seating plan is now available in the extent table. We would just iterate over it. Iterating is a bit exaggeration here because extent only has 1 row. So e.rows and e.calls will receive a single binding, the dimension, the extent of the seating plan. Okay, then we would enter the generation of the northwest and southeast corner just like we discussed on the slide. Okay, you see that there is a dependency here between e rows and this e rows. This is dependent iteration, so we are of course using the laterals here to express the dependent iteration. Okay, so that would be the generate part, and now to the testing part. Now that we know the northwest and southeast corner that has been generated, we could use these, yes, you can see here in predicates, to restrict a scan of the entire seating plan. This is our 15-row seating plan. We would restrict the scan of this entire seating plan to the rows and columns that lie within the current rectangle, the currently considered rectangle. Okay, so only those seats S will qualify that are inside this current rectangle. Okay, if this seat is not taken, if it's not taken, this is one of these qualified aggregates, then we would count it. Okay, so this would return a scalar. This would return a scalar, a single row, a single column table, a scalar that contains the number of seats that are not taken in the current rectangle. That is our filtering criterion. We would compare this to k. If this number of free seats indeed exceeds k or is at least k, that would be a qualifying rectangle. Found one. Okay. Since we found one, make a protocol. So record its northwest corner in this, as we were suggesting, the simple 2-column row value, and also compute its width and height, which is just the difference between the column and row values of the northwest and southeast corners. Done. We've got the upper left corner, we got the width and height of the qualifying rectangles. These are all the qualifying rectangles. They are stored in the rects table. All right. So let's see what comes out of this table rects. Not needed yet. Okay, so quite a number of rectangles qualify here. Yep. There's no doubt about this, that, for example, the rectangle starting in the upper left corner and 1,1 on the top left corner, and that has an extent that is as large as the entire seating plan, would fit the K. In the entire cinema, luckily, we would find 5 or k free seats. But hopefully we can find the smaller rectangle. And you see already in these entries that there are some of these rectangles have smaller seating areas. We try to identify these in the very last step. So get rid of this and re-enable the rest of the query, which is just the epilogue, the rest of the stuff that we have to do. We would just check all of our rectangles, whether their area, this would be the area, is indeed the minimum area of all rectangles. As you can see, this is a subquery that is a scalar subquery. It's a non-correlated scalar subquery. We would find the minimum seating area once here. That would yield a numeric value, the minimum seating area. And we would just filter for all the rectangles that have just this minimum area. And all of these would be printed and output as a result. And that would be a solution to the finding seats problem. There you go. In the top left corner, width 3, height 2, that should be one viable seating plan option for our friends. Okay, when you look at this file, you will see that there is other instances of the cinema prepared, larger seating plans and larger number of friends. I invite you to play with this. I invite you to maybe consider other ASCII or textual based encodings and try to parse these just in the side as we've done in the seats CTE. But this concludes our discussion of the finding seats example. It's quite a representative example of what you can expect in the rest of the lecture. Of course, the problems can get more interesting once we collect more cool stuff in the SQL language. And let me assure you, there's really a lot of more stuff that we can collect and use to good measure. I'm looking forward to discuss this stuff with you, starting with chapter 5. The videos will be published soon. I hope you will be around then. Looking forward to that. See you. Bye.